This valence shell electron pair repulsion theory was introduced by Sidwix and Powell. Later it was developed by Gillespie and Nyholm. Now here it was introduced by Sidwix and Powell, and later it was developed by the Gillespie and Nyholm. Here already we know about VB theory, valency bond theory, VBT. This VBT valency bond theory explained about geometry, bond length, bond angles, and bond energies. Based on VBT valency bond theory, valency unpaired electrons only participate in overlapping. SS overlapping, Sp overlapping, Pp overlapping. Among these, the extent of overlapping is more, bond strength also more. Pp overlapping is more than compared to Sp than compared to SS. Okay. Anyhow, here to explain the perfect geometry of the molecule according to VBT depends only on number of sigma bonds around the central metal atom, not on number of pi bonds. So pi bond is not decided its geometry. To explain geometry, pi bonded electrons or the orbitals do not participate to explain the geometry. Only sigma bonded electrons, sigma bonds. Anyhow, around the central metal atom, along with the sigma bonds, some pair of electrons are there. They are the non-bonded electron pairs are there. Due to the presence of non-bonded electron pairs, its geometry changes from regular shape to the irregular shape. According to VBT, valency bond theory, just VBT theory explain regular shape of the molecule. Regular shape of a molecule explained by this VB. Regular molecule means it contains only sigma bonded electrons. They are called a bonded electron pairs. They are bond pairs, pair of electrons. They are called a BP, bond pair of electrons. Here VBT valency bond theory just explain a regular shape, and it explain only presence of sigma bonded electrons, shape of the molecule explained. But according to valency shell electron pair repulsion, there is an important word or repulsion theory. According to this, due to the presence of non-bonded electrons, valency shell electron pair repulsion theory explained are the irregular shape of the molecule. To explain irregular shape of the molecule, it contains non-bonded these non-bonded electrons around CM, central atom, non-bonded electrons. These non-bonded electrons are called a lone pair of electrons, LP electrons. So to explain irregular shape of the molecule based on their pair of electrons, either bond pairs or the lone pairs, there are four people, Sedgwick, Powell, Gillespie, and Nyholm, created an important theory, that is valence shell electron pair repulsion theory. I'll take a simple example like this is AB3. I'll take like this. One model, one example. In this AB3 molecule, like one simple example. Now it is central atom of an element is A. Central element is A. And here B are the bonded atoms. In this bonded atom B, three are there around A central atom. Here three B atoms are bonded. 1, 2, 3 sigma bonds are there. They are the BP bond pair of electrons are 6 electrons and 3 pairs are present. And here there is no LP electrons, 0. No lone pairs, no LP electrons. Certain geometry is there. Here I'll take one more example is AB3E model. Here E indicates one lone pair is there. Now here A central atom, here it contains one lone pair, and here B and B and it is B, 3 bonded. It is a LP, lone pair of electrons. Here 3 sigma bonds are there, and 3 bond pairs, and 1 is lone pair is there. Total 4 pairs are there. Here comparing these two examples. Now AB3 and AB3E, here both are even though having same hybridization. I'll explain that hybridization concept. It is a regular in shape, It is irregular in shape. So to explain that regular and irregular shape, this theory by these 4 people introduced some important postulates. According to this theory, v.s.e.p.r.t theory, according to valence shell electron pair repulsion theory, if the central atom of an element like AB3E, if the central atom of an element has at least one lone pair, this is the lone pair, this is the E means lone pair. Now remaining 3 are the bond pairs, here B and here B and here B. This is sigma bond, and sigma bond. Now it is a LP, a lone pair. This a lone pair occupied space is more. Occupied space is more space. Space is more or occupied space, more space occupied by LP electrons. because these electrons are concentrated at one area, particularly at one nucleus, where it has bond pair A and A. That bond pair is formed by one sigma covalent bond. That sigma covalent bond is formed by mutual contribution, mutual sharing. This one electron pair is equally shared by this nucleus, A atom nucleus and B atom nucleus. And also your A atom and B atom nucleus. Here also A atom and B atom nucleus. That's why this sigma or the bond pair BP are the less space occupied by bond pair BP electrons, because the pair of electrons shared between two atoms of a nucleus. So due to the presence of these two atoms nucleus, this bond pair is equally shared and equally contributed, equally shared. That's why occupied space by bond pair is less. Less occupied space is nothing but they are more stable and has a less amount of energy, minimum energy. Whereas in case of lone pairs, this pair occupied at one area on particularly central atom occupies more space. Space is more, occupied space is more. Stability is less. Less stable means as high energy, more energy. So according to this, to stabilize, to get the stable molecule or to get the minimum energy and more stable, these electron pairs, lone pair and bond pair, there is a repulsion. And bond pair, there is a repulsion takes place. And bond pair, again lone pair, repulsions takes place. So regularly here AB3 molecule is a regular order. This regular order changes to irregular order. That is due to the presence of this lone pair of electrons. So in this irregular shape, AB3E type, due to the presence of one lone pair, its shape changes from a regular order to irregular order. Now, here lone pair, if it is contains two lone pair, that repulsive forces order is very important order. LP and LP electron repulsions generally greater than compared to LP and BP bond pair. It is greater than BP and BP electron pairs. So if the molecule containing central atom contain lone pair and lone pair, two lone pairs are there, repulsive forces are more distorted changes from regular to irregular, bond angle changes, and its shape also changes. I will explain that. And compared to the lone pair, bond pair repulsions are less. Compared to lone pair and bond pair, repulsions are again less. Based on this, I'll take one simple example and I will explain difference, variation. Okay, shape, how it changes. So based on these lone pairs, bond pairs, its shape, bond angle, and its bond energy, total parameters changes, bond length. So to explain particularly geometry of a molecule according to VB theory, only explain the normal regular shape, but valential electron pair repulsion theory explain a perfect geometry of the molecules. Okay, I'll take one simple example, that is CH4 molecule, methane. And I'll take your NH3 molecule, NH3. And one more example is water, H2O molecule, 3 molecules. Here, in this case, methane molecule, central atom of element is carbon. Around carbon, 4 valence electrons are there. These 4 valence electrons are bonded with 4 hydrogen atoms which are tetrahedrally bonded, like tetrahedral shape like this. That is mutual contribution, mutual sharing takes place. Then it forms a like tetrahedral shape. I'll explain shapes and bond angles and everything after a hybridization concept. The central atom of an element around the central, your bond pair are 4 bond pair, they are the sigma bonds. LP electrons are 0. There is no LP, lone pairs. Now here between carbon hydrogen bond angle is bond angle BA is 109 degrees 28 minutes. And its shape is tetrahedral shape. Tetrahedral. And its hybridization is Sp3 hybridization. Now, once we can observe this methane molecule, it is 15th group element and it contains one lone pair on nitrogen atom. Nitrogen containing 5 valence electrons out of 5. Here 3 are bonded with 3 hydrogen atoms. Hydrogen atom. And one is lone pair is present on nitrogen atom. Now here LP is equals to 1, BP bond to pair are 3, means 3 sigma bonds, 1 lone pair. Now here bond angle is BA is equals to 107 degrees. Geometry is pyramidal geometry and its hybridization is Sp3 hybridization. I'll explain that how it forms hybrid orbitals. Then here in water molecules, central atom of element is oxygen. 6 valence electrons are there out of 6. Here 2 pairs are there. This is a lone pair and it is also a lone pair. 2 are the bond to pair are there. Now your bond angle is 105 degrees. Now this is your bond to pairs are 2 sigma bonds and LP lone pairs are also 2 pairs are there. Now here the BA bond angle is 105 degrees. And shape is bent shape or V shape. This is V shape. And here the oxygen undergoes a Sp3 hybridization. So after hybridization, we'll get the clear picture about valence shell electron pair repulsion theory. Once we can observe here in this CH4 molecule only here bond to pair and bond to pair repulsions only present here. Bond pairs and bond pairs. Here lone pairs and bond pair repulsions are there as well as bond pair and bond pair repulsions are there. Here lone pair is there. Here a lone pair and bond pair repulsions are there and also bond pair and bond pair repulsions are there. So by using valence shell electron pair repulsion theory, here in this bond pair and bond pair repulsions are very less because of absence of lone pair, 0 lone pair. There is no such a repulsions to minimize the energy to get the regular order. There is no repulsion. That's why is a regular shape is tetrahedral shape and its bond angle is 109 degrees 28 minutes. Whereas in this case ammonia NH3 Due to the presence of one lone pair and bond pair repulsions are there, and also bond pair and bond pair repulsions are also present. So compared to this bond pair and bond pair lone pair repulsions are more than compared to bond pair and bond pairs. Whereas in this case, two lone pairs are there. Number of lone pairs increase here. That lone pair and lone pair repulsions are greater than compared to lone pair and bond pair than compared to bond pair and bond pair, according to valence shell electron pair repulsion theory. Once we can observe all the three examples, number of lone pairs increases, its bond angle decreases, a regular tetrahedral shape changes to a irregular distorted order, that is based on their number of lone pairs, its geometry change, that is tetrahedral to a pyramidal, and again number of lone pair increase the pyramidal to a bent or the V shape. So based on hybridization concept in all the three examples, central atom of an element undergoes sp3, sp3, sp3. Hybridization is same, but its geometry change. That is due to the presence of lone pairs, bond pairs, lone pairs, and bond pair repulsive forces. Based on this, we'll get clarity about pair of electrons influences the shape of molecules. According to VB theory, general regular shape explained only by using sigma bonded electrons, not by pi bonds. But it doesn't explain any information about a pair of electrons, lone pairs and bond pairs. Only regular shape explained. So after that, VB theory, VB theory is modified by 4 people under the name of valence shell electron pair repulsion theory to explain irregular shapes of the molecule due to the presence of pair of electron, that is a lone pair, bond pair, and bond pair, and lone pairs. Okay. So here, based on this lone pair and bond pairs, shapes and bond angles changes. Based on these theories, I'll create one important table based on lone pairs and bond pairs, and I'll give the shape of the molecules, and I'll give 1 or 2 examples based on this concept VB theory, v.s.e.p.r.t theory, and hybridization. Now regularly one question, which of the following is isostructural molecular pair they will create among this pair, which is isostructural and isoelectronic species? Such questions regularly they are asking in examination objective. So anyhow, here the one type of molecule, one type, and your number of BP bond pairs, and your number of LP lone pair of electrons, and your the shape of the molecule. Then example for this. Example for the type of molecule. The first example is AB2 type model. Yeah, there is no electrons, we can take E0, no lone pairs. All are the bond pairs only. It is the central atom of an element. Around central atom of an element, A, and it is B, and it is B. Now here AB and AB, there is no lone pairs, only 2 sigma bonds are there. That's why your bond pairs are 2, lone pairs are 0. Shape of the molecule is a linear shape. Like this is a linear shape, like carbon dioxide, BeCl2, or BeF2, like examples. Linear in shape molecule this is. like your AB3 model without any lone pairs. Number of bond pairs are 3, lone pairs 0. Your trigonal planar for this O3 molecule, sorry, your BCl3, your v.s.e.p.r.t like examples. Now, in this second example, there is no such a lone pairs E not 0, no lone pairs, 3 bond pairs only. Now here the AB4 molecule, here 4 bond pairs, lone pairs 0, regular shape is tetrahedral shape. Now for this CH4, now here SiH4 like CCl4 carbon tetrachloride, and also all alkanes, each carbon atom undergoes like tetrahedral shape, like bond pairs are 4. AB5 molecule, 5 are there, lone pairs are 0. It is bipyramidal structure, that is trigonal bipyramidal structure. Now phosphorus pentachloride, phosphorus pentafluoride and phosphorus pentachloride. Now here AB6 model, no lone pair, 6 bond pairs only. Your lone pairs are 0. Geometry is octahedral geometry. Now sulfur hexafluoride like examples. So here these 5 examples. Here the 1, 2, 3, 4, 5 example. All these model, there is no lone pairs. All are having regular shape without any disorder, distorted shapes. Now I'll take here with the lone pairs like AB2E model like this. AB2 means central atom of element is A. Now here B and B, but it contains one lone pair. Due to the presence of this lone pair and bond pair, lone pair and bond pair, yeah, there is no such a repulsion. Only bond pairs linearly takes place. But due to the presence of this lone pair and bond pair, lone pair, bond pair, repulsions, bond angle reduces from here 180 degrees to certain angle reduces. So with increasing number of lone pair, its bond angle decreases, and the shape also changes from regular to a irregular shape. It contains 1 lone pair. Here bond pairs are 2, lone pair is 1. Its geometry is bent shape like here SO2, O3 like examples. Now under this lone pair concept, AB to E2 model, 2 lone pairs, general example is here bond pairs are 2, lone pairs are 2. Here also V shape, or also we can use as a bent like structure. Best example is water molecule H2O, 16th group elements. Now here AB3E model. Now bond pairs are 3, lone pair is 1. Now it is a pyramidal structure, pyramidal shape. Best example is NH3, ammonia molecule. It contains 1 lone pair. Now here the AB3E2 model, 2 lone pairs are there, bond pairs are 3, lone pairs are 2 here. Now 2 lone pairs and bond pairs are 3 are present for this. Now it is trigonal, or we can use C structure it is. Now for this ClF3, here it contain like seesaw structure. Also we can use it is T shape. It is T shape. We can use this. Yeah, the ClF3. Now, again it is your AB4E type model. Your bond pairs are 4, lone pairs are only 1. Your example is square pyramidal structure. Square pyramidal structure. I'll give example here. Our AB4 and E2 model, 2 lone pairs are present here. Bond pairs are 4 bond pairs and 2 lone pairs. It is square planar structure. Now for this XEF for example, your square pyramidal structure it is. Square pyramidal structure. It is we can take SEF bond pairs and one is a lone pair. SF4 we can take one lone pair is present here. Then here AB5 model, AB5E type model, one lone pair is present here. Bond pairs are 5, one is a lone pair. Now it contains example is BRF5 like this. Now around BR 7 valence electrons are there like this, and here bond pair of electrons are present like this. 5 bond pair of electrons are present. It is now like this structure is present. Like here based on number of lone pairs and bond pairs up to here 5 models. Yeah, there is no lone pairs, all are bond pairs only present, all are 0 0 up to here lone pairs, but bond pairs are 2 3 4 5 6. Then here number of lone pairs increases, their bond angle and the shape also changes. After valence shell electron pair repulsion theory, after hybridization concept, we'll get clarity, clear information about isostructural or isoelectronic species. There is one shortcut formula to find out hybridization of central atom of an element. With the help of this, easy to estimate its geometry, shape, or bond angles, number of lone pairs and bond pairs, and its hybridization concept. Okay. Say hybridization. One of the most important concepts here. We can expect one question on the basis of hybridization. So here, before hybridization, based on VB theory and valence shell electron pair repulsion theory, regular and irregular geometry is explained. Here also in hybridization, with the help of intermixing of atomic orbitals of a central atom of an element. Such atomic orbital either may be a off-filled or a completely filled or vacant orbitals or involved atomic orbitals in hybridization. On the basis of intermixing of atomic orbitals, it gives the corresponding hybridized orbitals. So this hybridization concept was introduced and explained by Pauling. To explain clear geometry, bond angle, and bond lengths, some parameters of the molecules. Here, in this hybridization concept, central atom of an element, central atom present in a molecule, your central atom present in a molecule contain atomic orbitals, almost same energy, atomic orbitals, involve in intermixing to give same number of hybrid orbitals. So are the central atom present in a molecule contain atomic orbital, such atomic orbital almost all having the same energy, we are involved in intermixing to give the same number of identical hybrid orbitals. That is intermixing of atomic orbitals present in a molecule or a species, either a positive or negative ion or a neutral molecule, gives the same number of identical hybrid orbitals. For example, central atom of element one s orbital and one p orbital intermix gives two sp hybrid orbitals. This is hybrid orbital HO. These two are AO, atomic orbitals. Now, one s orbital and two p orbital undergo intermixing. It gives 3 sp2 hybrid orbitals. Your sp3 are there. Now it gives 4 sp3 hybrid orbitals. Now here the s1, p only 2 are there, one d is there. Then here we'll get 4 dsp2 hybrid orbitals and so on. If it is 1 s orbital and 3 p orbital and 1 d orbital, is there a total how many atomic orbitals? 1, 2, 3, 4, 5. Same number of hybrid orbitals, means it gives 5 sp3d hybrid orbitals. If it is s, 3 p orbitals and 2 d orbitals are present, it gives 6 sp3d2 hybrid orbitals. S1, P3, 3p orbitals and d orbitals are 3 are there. It is sp3d2 hybrid orbitals. So how many atomic orbitals are intermixed? Same number of hybrid orbitals are formed. Here 7 hybrid orbitals are formed. So in this manner, number of atomic orbitals are hybridized or intermixed with each other and give the same number of hybrid orbitals. First, I will take one simple example, that is sp hybridized. In one molecule, the central atom of an element involve only one s orbital. This is the spherical shape, and one is p orbital. This is the p orbital is a dumbbell shape. This is the internuclear axis. Now this is the internuclear axis of the p orbital. One s orbital, that is ns. This is the np. Your n start with 2, 3, 4, 5 and so on. Your n start with 1, 2, 3, 4, 5 and so on. Now these two are intermixed, almost all same energy atomic orbitals. It forms, this is the nucleus of central atom of an element. This is the sp, and this is also a sp. Now this is the equal parts. The sharing equally shares. This is the intermixing of two atomic orbitals which containing a central atom of element and give the same number of hybridized orbitals. This is the sp1 and it is also a sp1. The two hybridized orbitals are formed. Now, due to the operation of these two hybridized orbital to form hybridized orbital, your atomic orbitals may be contain, maybe half filled or completely filled or vacant. Vacant orbitals are also lone pair, LP electrons are also participated. But pi bonded orbitals do not involve in intermixing or in hybridization. Okay, this is the very important point. So an s orbital and one p orbital undergo intermix, it gives the two same identical hybridized orbitals. If it is one s orbital and two p orbital undergo intermix, how it intermix I'll show here. Listen here. Now here the one s orbital and two p orbitals, like this is px and this is py, maybe this is the py. So are the s orbital and px py, two p orbital against central atom of an element. Here it is sp2 like this. This is the sp2, here sp2 and here in sp2 hybridization. So here the each orbital sp2, all the three sp2 hybridized orbitals are having the same energy and having all the three having same shape of the molecule. The same energy and same shape of the molecule decides. And based on their hybridization, based on their lone pair concept, we can decide its geometry of the molecule. If it is one s orbital and three p orbitals undergo intermix, here it is s, it is px, it is py and it is pz. Here four separate nucleuses are there, like p orbital and s orbital. Finally, it gives only one central atom of an element, like sp3. Here four hybridized orbitals. Here it is sp3, and it is sp3 like this. How many atomic orbitals are intermixing here? 4 atomic orbitals are intermixing. Again, the 4 same number of hybridized orbitals. Now, in this case, here the percentage of S character and percentage of P character. How much S and how much P percentage present. In SP hybridization, here we'll get total is 2 atomic orbital. Percentage means 100, 50 percentage. Means S percentage is 50 and P percentage is 50 because S1, P1. Each one is 50 into 1, that is 50 into 1, that is each one 50 percentage is present. Clear? Means in terms of fraction, 1 by 2 of S character plus 1 by 2 of P character also we can. Because total how many are there? 2. S only 1, P only 1. That's all. Same thing, Sp2. Yeah, we can take percent means 100 divided by 3. Each one is 33.33 percentage. Each one. Yes, only 1 is there. That's why 33.33 into 1. That is Sp is 33.33 into 2. That is 66.66 percentage. In terms of fraction, we can take 1 by 3 parts or 1 by 3 of S character and 2 by 3 of P character. Similarly, in Sp3, 1 plus 3, 4 are there. Total 100 divided by 4, that is each one 25 percentage. S percentage is 25 and P percentage is 75 percentage. In terms of fraction, we can take 1 by 4 parts of S character and 3 by 4 percentage parts of P character. So in this manner, in hybridization concept, we'll create an important table based on their hybridized orbitals, number of lone pairs and bond pairs, and also shape of the molecule and bond angles also we create. Just observe it. Percentage of S character, P character, everything will create an important table. Just observe it. Type of hybridized orbitals. Hybrid orbitals. This is type. And here percentage of S character, percentage of P character, percentage of D character, your shape of the molecule, or take bond angle, finally shape of the molecule. One important shape and example and shape of the molecule. The type of hybridization is Sp. S character is 50%, P character is 50%, it is the 0%. For this bond angle is 180 degrees. For this example is BeCl2 or BeF2 carbon dioxide Sp hybridization. Now here shape of the molecule is a linear shape. Like a linear means central atom of element is AB. Like your AB2 type, like there is no lone pairs, your bond angle is 180 degrees. There is no lone pair. Like your beryllium, central atom of element is beryllium, your fluorine and your fluorine. Beryllium, chloride and chloride, this is carbon dioxide, C double bond O, C double bond O. Your sigma bonds only participated. Already explained to you, there is no pi bonded orbitals do not involve. That is the first one. Like Sp2 hybridization, here already how to calculate explain to you. This is 100 divided by 2 each one for each. Yeah, 100 divided by 3. Now it is 33.33 or 66.66. 0% here. Bond angle is 120 degrees. Like boron trifluoride, boron trichloride, like this is. Now your T planar structure, trigonal planar structure. This trigonal planar structure means your boron 3 fluorine atoms are bonded like. Now this is trigonal planar structure of the molecule. Okay. Now your sp3 hybridization, here 100 divided by 4 because 1 plus 3 4 hybridized atomic orbitals, each one here 25 percentage, here 25 into 3 75 percentage, and it is 0 percentage. Here 109 degrees 28 minutes, like CH4 example, like SiH4, like CCl4 example. Around carbon, 4 bonds are tetrahedrally bonded. So our shape is tetrahedral shape. It is. Shape of the molecule is tetrahedral. So under this, one more important case is DSP2. It also 100 by 4 it is. Yeah, D1, S1 and P2. That's why S is only one. That's why 25 percentage. 50 percentage. Now D started. That is again 25 percentage. Now it is bond angle is square planar structure. It is bond angle is 90 degrees. Now example is Cu and H3 taken for one complex ion like +2. Or your NiCN taken for -2. Now it has a square planar structure. Square planar. Similarly, here one more important example is here. Here sp3d is there, d1 is there. Here 1 plus 3 plus 5 are there. That's where 100 divided by 5, that is each one 20 percentage. Here 60 percentage is P, 3 are there, D is only 120 percentage. Here bond angles 2 are there, 120 and 90 degrees. Example is phosphorus pentachloride or phosphorus pentafluoride. Its geometry is trigonal bipyramidal structure. This is. It has 2 important structures already in p block elements given here in this PCl5 structure. Structure of PCl5, there are 2 important bond angles are there, equatorial and axial bond angles. Like here, one more important example is there here on the basis of hybridization concepts. That important example is here sp3 d2 or d2 sp3 hybridization. Here total here 1 plus 3 4 plus 6 are there. That's why here 100 divided by 6. Now nearly each one get 16.6 each one is, and D2 are there, P3 are there, 66.6 into 3. D is 16.6 into 2 like. Here bond angle is 90 degrees here. Here example is SF6 or some complex compounds are there. Geometry is octahedral complexes. In coordination compounds in second year we'll get a story about this. It is outer complex, it is inner complex. Low spin and high spin complexes are there. In coordination compounds we'll explain geometry of complex compounds. So on the basis of this table, by using one simple shortcut to explain the hybridization, for neutral molecule or any ion, molecular ion, either positive or negative ion, there is one important shortcut. That shortcut is most important shortcuts. Based on that important shortcuts, easy to estimate its hybridization, and by using this table, will create easily one of the most important structure, number of lone pairs and bond pairs. In examination regularly they'll ask based on these isostructural number of lone pairs and bond pairs. For neutral molecule, for neutral molecules, number of total number of hybrid orbitals is equals to total number of bond pairs plus total number of lone pairs sp. This is one of the most important formula. If you know the molecule central atom of an element and around the central metal atom of an element, how many bond pairs, how many lone pairs, how to calculate its hybridization. Next, one more last important hybrid orbitals equal to 1 by 2 into v plus m minus c plus a. This is the very, very important formula. This is for all species. For all species. For all species means either for neutral molecule or ions. Ions means either maybe a cations or anions. For all these, easy to calculate its hybrid orbitals. If you know hybrid orbital, then easy to calculate its shape of the molecule. Now here V is number of valency electrons of central elements, and here M is number of monovalented, only monovalented elements around the central elements, around the central element. Then here C is charge on cation, charge on cation, and A is charge on anion. Okay, so better remember these two important formulas. On the basis of these two important formulas, tomorrow better keep on side one neat previous year questions assignment. We'll solve the maximum number of questions on the basis of three theories: v.s.e.p.r.t, v.s.e.p.r.t theory, and hybridization. Okay, thank you. Take care.